Hello. Hello and welcome to the chapter 5 of combinatorics or permutation combination specifically as you would know it. We have finished polynomials and Cherif equations. We will spend a few days on going through the theory. So grab pen and paper if you want to make notes, specifically for the formulas and the derivations. And let's get started. So mostly it will be a read through and I'll explain things where things are to be explained. So you can read along with me. In this chapter, we will study basic principles of counting, permutations, and combinations. This study will enable you to further study the branch of mathematics called combinatorics. You would have certainly encountered a combinatorical problem in your life. It would be really surprising if you have not. Have you ever solved a Sudoku puzzle or Rubik's Cube? Have you ever counted the number of poker hands that are full houses in order to determine the odds against a full house? A very simple example I could give you is that you might have seen the suitcases with those number locks. There are 3 rings, 0 to 9. So that is one example of how many permutations you can have. Okay. Or let's see. Okay. Have you ever attempted to trace through a network without removing your pencil from paper and without tracing any part of network more than once? These are all combinatorical problems. As you can see that combinatorics has evolved from mathematical games. With the invention of modern computers, we are enabled to solve more and more problems of combinatorics which were earlier not feasible due to calculations involved. The computer programs are often based on combinatorical algorithms which determine the speed and efficiency of the solution. Analysis of these programs and algorithms require sound knowledge of combinatorical mathematics and thinking. In computer science, we write test cases for our programs, and those test cases can be enumerated by applying permutations and combinations on input data and states produced in the program. Combinatorics is a powerful tool for making sure that the tester does not miss any test case, which in mission critical programs is of paramount importance. So we'll skip this and let's get started with the section 5.1. So the first thing is that there are 4 basic counting principles. Okay. So it requires that you know such theory. If you don't know such theory, then you can't proceed. Okay. Theory is explained with the help of such theory. If you have not studied such theory, go ahead and study such theory and then come back to this. Let S be a set. A partition of S is the collection of S1, S2 up to Sm of subsets of S such that each element in S is exactly one of these subsets. So S is union of S1, S2 and so on through Sm. And the intersection of 2 subsets is phi, or rather intersection of 2 subsets is phi. Thus the sets S1, S2, S3 are pairwise disjoint sets, and their union is S. The subsets S1, S2 through Sm are called the parts of the partition. Note that by definition, a part of the partition may be empty, but usually there is no advantage in considering partitions with one or more empty sets. The number of objects of a set S is denoted by mod S, and this is called the size of S. Looks like mod, that is why I'm reading it mod. Okay, I'm not sure if I can read it something else. I'll call it size of S. Okay, I'll call it size of S. So first principle is the counting principle, that is the counting or addition. The addition principle is what it is. Suppose that S is partitioned into pairwise disjoint parts. There is a typing mistake, parts. S1, S2 through Sm. The number of objects in S can be determined by finding the number of objects in each of the parts and adding the numbers so obtained. So size of S is sum of sizes of each part. If the sets S1, S2, Sm are allowed to overlap, then a more profound principle, the inclusion-exclusion principle, can be used to count the number of objects in S. We need to be careful when partitioning S into too many parts. For example, if you partition S into parts in such a way that each part contains only one element, then addition principle becomes, no, S should not be there, becomes counting the number of parts, which is basically same as listing all objects of S. Thus, the art of applying addition principle is to partition the set into not too many parts. An example is given. In a university, there are 4 mathematics courses, 2 economics courses, and 3 literature courses. A student is allowed to enroll into 1 course at most. Thus, we see that a student can take a course in 4 plus 2 plus 3 is equal to 9 ways. Next principle is multiplication principle, which will be stated for 2 sets, but it can be generalized for any infinite number of sets. The multiplication principle states that let S be a set of order pair AB, where the first object comes from a set of size P, and for each choice of object A, there are Q choices for object B. Then the size of S is P times Q. So size of S is P times Q. As in basic arithmetic principle is repeated addition, similarly multiplication principle is actually a consequence of addition principle, that is repeated addition. Let A1, A2 through AP be P different choices for object A. We partition S into parts S1, S2 through SP, where SI is the set of ordered pairs in S, with first object AI. The size of SI is Q, hence by the addition principle, size of S is equal to size of S1 plus size of S2 and so on through SP. So sum of sizes of each part. So we add Q P times and then we have P into Q. The multiplication principle can be stated in another way as, if a first task has P outcomes and no matter what the outcome of the first task, the second task has Q outcomes, that is, outcome for 2 tasks are mutually exclusive, then the 2 tasks can be performed in P times Q outcomes. So there are some examples given. First example is pencil comes in 2 different lengths, 4 different hardnesses, and 3 different thickness. How many different types of pencils are there? So the answer is the pencil has 3 different properties which are exclusive of each other, and thus we can apply multiplication principle. Hence, number of different types of pencils is 2 times 4 times 3, that is 24. The number of ways a man, woman, boy, and girl can be selected from 3 men, 3 women, 5 boys, and 4 girls is 3 times 3 times 5 times 4, that is 180. Next example is determine the number of positive integers that are factors of the number 2 to the power 3 into 3 to the power 4 into 5 to the power 5 into 7 to the power 7. The numbers 2, 3, 5, 7 are prime numbers. By the fundamental theorem of arithmetic, each factor is of the form 2 to the power I, 3 to the power j, 5 to the power k into 7 to the power l, where the ranges are written here. There are 3 choices for I, 4 for j, 6 for k, and 8 for l. So by multiplication principle, the number of factors is 3 times 4 times 6 times 8. That is, when all I, j, k, l are taken as 0, then we have 1 as the factor. The total number of factors is 576. In the multiplication principle, the Q choices for object B may vary with the choices of A. The only requirement is that there be the same number queue of choices, not necessarily the same choices. So another example is how many two-digit numbers have distinct and non-zero digits. So the answer is a two-digit number AB can be regarded as an ordered pair AB, where A is the tens digit and B is the units digit. Both are not allowed to be zero and they must be different. Thus, we see that there are 9 ways to choose A, which are 0 through 9. Once A is chosen, we cannot use the same digit for B, which means we are left with the 8 choices for B. Here we see that choice of A makes a difference on what choice B has. However, for multiplication principle to be applicable, what matters is that number of choices remain constant, which is 8 in this case. Applying the multiplication principle, we arrive at the answer of the question as 9 times 8 is equal to 72. There is another way to arrive at the same result. Total number of two-digit numbers is 90, 10, 11, 12 through 99. These 90 numbers, 9 have a 0 in them, that is 10, 20, 30, 90. And 9 have repeated digits, 11, 22 through 99. Thus, total number of required numbers equals 90 minus 9 minus 9 is equal to 72. We can derive two important ideas from the previous example. First is that it is possible to solve a counting problem in many ways. Second idea is that to find the number of objects in set A, in this case, this is again a typing mistake, the set of two-digit numbers with non-zero and distinct digits. It may be easier to find the number of objects in a larger set U containing S, the set of all two-digit numbers, and then subtract the number of objects of U that do not belong to A, the two-digit numbers containing 0 or repeated digits. This leads us to subtraction principle. So let A be a set and U be a larger set containing A. Then A bar is basically, it is written as U backslash A, but what you mean to say is that it is subtracted from set U. So X is in set U and X is not an element in set A. That is the meaning of this, that X is in the universal set but not in the set A. The complement of A in U. This is also read as complement of A. This A bar is read as complement of A. Sometimes it is denoted as A prime. So A prime is equal to U minus A. Then the number of, again number is misstepped. Give me a second. Let me quickly note down the typing mistake. Okay. It will not take long. So there was party and it becomes SA and we have number. So the set U is usually some natural set containing all the objects under discussion. It is called a universal set. Using the subtraction principle should be used only if it is easier to count the number of objects in U, and it should be and then that. And A prime, it should be easy to count the number of objects in U and A prime than to count the number of objects in A. Example is most websites on internet have a lower limit of 8 characters as password lengths. Suppose if these passwords are made up of digits 0 through 9 and lowercase numbers A through Z, then how many passwords will have repeated symbol? So there are a total of 10 digits, 26 letters and 36 symbols. So by applying multiplication principle, we have the size of universal set as 36 to the power 8. That's quite a big number. And then A prime is first we can choose first character of password we can choose in 36 ways. Then second we can choose in 35, third in 34. So this will guarantee us our unique password of 8 characters, which is also a quite big number. Then the size of A is basically U minus A prime, that is the main numbers. Okay. Now we come to division principle. Let S be a finite set is partitioned into k parts in such a way that each part contains the same number of objects. Then the number of parts in the partition is given by the rule k is equal to size of S divided by number of objects in a part. An example is there are 240 rats in a collection of cages. If each cage contains 2 rats, the number of cages equals 240 by 2 is equal to 120. Interesting problems of division principle can be found in the problem section. Most counting problems can be classified as one of the following types. Count the number of order arrangements or order selection of objects without repeating any object. With the repetition of objects permitted, limited repetition, that is, count the number of unordered arrangements or unordered selection of objects without repeating any object with repetition of objects permitted. We can represent repetition and non-repetition of objects as selections from a set and a multi-set. The latter might prove to be more useful in some cases. A multi-set is like a set except that its members need not be distinct. For example, a multi-set M with 3 A's, 2 B's, that is 5 elements of 2 different types. We usually indicate a multi-set by specifying the number of times different types of elements occur in it. So M is denoted by 3.A, 2.B. The number 3 and 2 are the repetition numbers of multiset N. Thus, we can extrapolate that a set is a multiset with all repetition numbers equal to 1. Often, there is no limit on number of repetitions, that is, infinite repetitions are allowed. So, there are 3 footnotes which you can read. So, footnote 1, which was here, when we talked about non-distinct elements. Thus, a cardinal root of sets is broken by multisets because the set is not supposed to have duplicates or repeated elements. The set AAB is same as the set AB, but not so for multisets. In standard set theory notation, we could denote the multiset M using ordered pairs as like this. And about infinity, in no circumstances we need to consider different sizes of infinity. Now I will go through factorial of n. Factorial of n is denoted by n exclamation mark. In the old style, it is written like this. And then there is a period, it is not multiplied. N factorial is given by the first n natural numbers, that is, n factorial is equal to 1, 2, 3, 4 up to n. And 0 factorial is 1. We'll see its proof. Okay. Permutation means arrangement of objects along with selection in the permutation of object order matter. If order of object changes, then the permutation also changes. Combination of objects means selection of objects in such a way that order does not matter. So we now go through permutation. Let me see if we can complete this. Yeah, let's do permutation and combination. Let R be element of set of positive numbers. By an R permutation of a set of n elements, the meaning of an ordered, by definition of permutation, arrangement of R in the set of n elements, R less than equal to n. If S is equal to ABC, then the 3 1 permutations of set are ABC. The 6 2 permutation of S are AB, AC, BA, BC, CA, AB. That is, we are selecting 2 elements at a time. In this case, we are selecting 1 only. And the 3 permutation of set S are ABC, ACB, BAC, BCA, BAB, and CBA. There are no 4 permutations of S because that will violate the assumption that R less than equal to n. The R permutations of an element of an n element that is denoted by P and R like this. or NPR like this, or like this, or like this. Okay. If R greater than 1, then NPR is equal to 0. Clearly, NP1 is equal to N for each N in a set of positive integers. If N and R are positive integers with R less than equal to N, then NPR is written as N times N minus 1 times so on through N minus R plus 1. Permutation of N objects taken R at a time is equivalent of filling R different vacant spots from N different objects. We can fill the first spot by N ways, second spot can be filled by remaining objects, that is N minus 1 ways, and proceeding this way we find that Rth spot can be filled in N minus R plus 1th ways. The total number is given here, and then what we do is we proceed after this, we take N minus R and so on up to 1, and we divide by the same amount. So our NPR, permutation of R objects out of N, is written as N factorial by N minus R factorial. Alternatively, first place can be filled in N ways, rest of R minus spots from N minus 1 objects can be filled in R minus 1 permutation of N minus 1, that is NPR is equal to N into N minus 1 PR R minus 1. Similarly, N minus 1 PR minus 1 is equal to N minus 1 into N minus 2 PR minus 2. Proceeding this way, we find that N minus R plus 1 P1 is equal to N minus R plus 1. Multiplying and cancelling, we do the same thing. We arrive here. The number of permutation of N elements is NPN is equal to N factorial. If you follow first here, then it is evident that 0 factorial is equal to 1. Meaning of 1 by minus k factorial, where k is in the set of positive integers. We have NPR is equal to N factorial by N minus R factorial. Putting R is equal to N plus k, we have NPN plus k is equal to N factorial by minus k factorial. But the number of ways of arranging N plus 1 objects out of N different objects is equal to 0. That is 1 minus k factorial is equal to 0. Although minus k factorial has no meaning by definition of factorial, but if we consider the above result, then the formula of permutation becomes valid even for R greater than 1. So I think I will stop here, and in the next video, we will cover circular permutation and other things, because I don't want to make a very long video, and it will be covered in 4 or 5 videos at most. Okay. So we are at page number 148, and we have to go till 148 and 176. So 149, 148, and we have to go till 163. So 15 more pages are there. It will take a while because I would like to go slow. And let me know if you want to go. Let me know if you want me to cover more on the in one video. If you want, I can make a longer video. I hope that you enjoyed this video and the read through. And in the next video, we will resume with circular permutation. So stay tuned. It will come tomorrow. I upload a video daily on mathematics. I upload actually quite a few videos, but for the math playlist, I upload one. So thanks a lot for watching the video, and go ahead and read ahead if you want. And if you have any doubts, let me know in comments. If you have feedback or suggestion, also then let me know in the comments. Thank you again for watching the video. Enjoy.